Hello everyone, welcome to Abdemi. I am Dr. Nandita and today I am here in the short lecture to solve some numerical problems based on the concept that you have learned in the chapter Chemical Equilibrium. Now what is chemical equilibrium? Now suppose if a liquid is evaporating in a closed container, some of the molecules, liquid molecules which are having higher kinetic energies are escaping from the liquid surface into the vapor phase. Now again it can also happen that some of the molecules from the vapor phase can strike the liquid surface again and will be retained in the liquid phase. Now it gives rise to a constant vapor pressure and we can say that the system has reached the equilibrium state where the number of liquid molecules which are escaping from the liquid phase to the gaseous phase and the number of molecules which are again coming back to the liquid surface are equal. Then only we can say that an equilibrium state has been reached. Now this chemical equilibrium finds applications in environmental processes as well as some biological processes. So it is very important to have the concept of this kind of equilibrium, right? So for example, if you consider that oxygen molecules and equilibrium between oxygen molecules and the protein hemoglobin, it is actually playing an important role when you are considering the transportation and delivery of oxygen molecules from our lungs to our muscles. Also, the similar equilibria between carbon monoxide molecules and the hemoglobin also find application in the toxicity of carbon monoxide molecules. So, from the examples I have given, you can easily understand that basic understanding about chemical equilibrium is highly required in order to understand the environmental processes as well as biological processes. Now with that, let's move on to the problem. So problem 1 is asking to say that a homogeneous ideal gaseous reaction AB2 gas to A gas plus 2B gas is carried out in a 25-liter flask at 27 degrees C. The initial amount of AB2 was 1 mole and the equilibrium pressure was 1.9 atmosphere. The value of Kp is x times 10 to the power minus 2. The value of x we have to find out. Now let's see how can we do that. So first of all, let's write down the equation once more. So AB2 gas is giving you in equilibrium condition A gas plus 2B gas, right? Now initially, that means at T is equal to 0, the number of the mole of AB2, that is the reactant, is 1 mole and we don't have any product, so number of moles of products are 0. Now at equilibrium we can write the number of moles as 1 minus x. Some of the reactants are already reacting and here it is x and it is 2x because 1 mole of A is generated and 2 moles of B are generated. So now from here we can write down the total number of moles as 1 minus x plus 2x, which is giving you the total number of moles as 1 plus 2x. Now, what we know that the partial pressure is equal to total pressure times total number of moles. Right. So, we will keep that in mind now, and this will be required for further solving this problem. Before that, we can write, what can we write? At equilibrium, we can write that PV is equal to, for ideal gas, PV is equal to nRT, we know that, and N is the number of moles here, P is the pressure, V is the volume, R is the ideal gas constant, and T is the temperature. So, in place of N, what can we write? We have found out that the total number of moles is 1 plus 2x, right, times RT. This is giving you the 1 plus 2x as PV by RT, and let's see what are the values that are given. P is given as 1.9 atmosphere, V is 25 liter, right? R is the ideal gas constant, we can write it as 0.082 times liter atmosphere mole inverse Kelvin inverse. This is for R, and for T, the T is also given as 27 degrees C, which is in Kelvin 300 Kelvin. So, if you check the units, you can see that it is nothing but mole, right? So, this is giving you 1 plus 2x is equal to, if you calculate and solve the right hand part, you will get 1.93. From here, x will come out as 1.93 minus 1 divided by 2. This is giving you 0.465. This is the value of x, which will be required later. Now, we will write from the partial pressure expression, which is equal to total pressure times total number of moles. So, let's write down the partial pressures for all the reactants and products. So, for PaB2, what can we write? So, 1 minus x divided by 1 plus 2x, which is the total number of moles. Now, we can consider the total pressure at equilibrium, which has been given as 1.9 atmosphere as P, right? This is the total pressure. And similarly, we can write for the products as PA is equal to x divided by 1 plus 2x times P, and PB is equal to 2x divided by 1 plus 2x times P. These are the partial pressure expressions for all the reactants and products. Now, we have to go for the Kp expression, and for Kp for this reaction can be written as follows: P A times Pb square, because we have 2 moles of B as products, divided by PaB2. We have also 1 mole of reactant, right? Now, as we have obtained the expressions for all the partial pressures for all the reactants and products, we will just put the values, right? 1 minus, for PA we can write X divided by 1 plus 2X times P, right? This is for PA. And for PB, what can we write? We can write 2X divided by 1 plus 2X P square, because we have PB square, divided by PAB2. So 1 minus X divided by 1 plus 2X times P. Now we have to simplify this. So if you simplify, what you will get? You will get 4x cube P cube divided by 1 plus 2x cube times, this will go upside down. So 1 plus 2x divided by 1 minus 2x times P. So 1 P will cancel out from here and here. 1 plus 2x will cancel out from here and here, and we will end up with, so rest of the part we will do here. We will end up with 4x cube P square divided by 1 plus 2x square times 1 minus 2x, right? Now we know the value of x from here, so we will just put the value of x here. So 4x is our 0.465 cube, P we know 1.9, so 1.9 square divided by 1 plus 0.465 square times 1 minus 2 times 0.465. Now from here, if you calculate, this is our 1 and this is our 2. This is our 1, and if you calculate from here, you will get 0.7285. You can simplify or you can write it like the following way: 72.85 times 10 to the power minus 2, or you can write it as 73 times 10 to the power minus 2. So you can also write it like x times 10 to the power minus 2, and from here you will get your x as 73, which has been asked to calculate in this problem. So our x is nothing but 73. Very simple. So we have to just understand the concept and of equilibrium, and you just have to calculate the total number of moles and partial pressure expression. You have to write down them in a proper manner, and after putting the values, you will be able to get the result, the right result, very easy. So now with this, let's move on to the second problem. So this problem is asking to calculate, or it is saying that the equilibrium constants Kp1 and Kp2 for the reactions X gas to 2Y gas and Z. This is one reaction, and we can consider this the total pressure of this reaction as P1, and another reaction has been given as Z is giving you P plus Q. This is the second reaction, and we can consider the total pressure of this reaction as P2. And it is saying that Kp1 and Kp2 for these given reactions respectively, the ratio is 1:9. So Kp1 is to Kp2 is given as 1:9. If the degree of dissociation of X and Z be equal, then the ratio of the total pressure at this equilibria we have to calculate. So we have to basically calculate the ratio of P1 is to P2. So we have to calculate the ratio. Let's see how can we do that. So basically I will just divide these two equations and we will separately calculate the Kp1 and Kp2, and from there we will be able to get the P1 divided by P2. So let's solve for the first equation. So the first equation is X gas is giving you 2Y gas, right? At t is equal to 0, that is at initial time, we can say that X is 1 mole and definitely Y is 0 because no product has been formed at that point of time. At equilibrium, what can we write? We can write this as 1 minus alpha and this is as 2 alpha because 2 moles of Y is formed during this reaction, and your alpha is nothing but the degree of dissociation. Right. So from here we can easily calculate the total number of moles, which is equal to 1 minus alpha plus 2 alpha is equal to 1 plus alpha. This is the total number of moles for the equation. Now, from the partial pressure concept, as I have discussed in the previous problem, partial pressure we will calculate for both the reactants and products, and from there we will get the Kp1. So the partial pressure of the reactant, that is Px, is equal to total number of moles, that is 1 minus alpha by 1 plus alpha times P1. P1 is the total pressure of this reaction, and Py can be written as 1 minus I'm sorry, 2 alpha divided by 1 plus alpha times P1. From here, Kp1 can be written, Kp1 for this reaction can be written in the following manner: Py square divided by Px, because 2 moles of Y has been formed, and we have Py and Px, that is partial pressure of X and Y. From here we can easily put these values. So Py is 2 alpha divided by 1 plus alpha times P1, and we have to make a square of it, divided by Px is 1 minus alpha divided by 1 plus alpha times P1, right? Now if you solve and simplify, you will get 4 alpha square P1 divided by 1 minus alpha square, and it can also be written as 4 alpha square P1 because of the fact that alpha is much less than 1 in this case. The degree of dissociation is much less than 1. So our Kp1 has come out as 4 alpha square P1. Now let's do the similar thing with the second equation. So second equation is Z is giving you P plus Q. So at initial time, that is T is equal to 0, Z is 1 mole, P is 0 mole and Q is 0 mole. And at equilibrium, when equilibrium is existing or equilibrium is reached, we can again say that this is 1 minus alpha, this is alpha and this is alpha. So total number of moles here is equal to 1 minus alpha plus alpha plus alpha, which is giving you the value of 1 plus alpha, right? Now from here we will again write the partial pressure expressions for all the products and reactants, which is nothing but the total number of moles times total pressure. So we have already considered the total pressure of this reaction as P2. So partial pressures for these reactants and products for this particular reaction. So let's first do for Z. So Pz is equal to 1 minus alpha by 1 plus alpha times P2. This is the total pressure for this particular reaction. Pp, one of the products, is the partial pressure is alpha divided by 1 plus alpha times P2, and Pq is equal to alpha divided by 1 plus alpha times P2. The same, right? Okay, now from here, these are the partial pressure expressions. From here, we will write for the Kp2. And for this particular reaction, Kp2 can be written as Pp times Pq divided by Pz. So let's just put the values of Pp, Pq and Pz from the partial pressure expressions. So our Pp is alpha divided by 1 plus alpha P2. Again Pq is the same. So alpha divided by 1 plus alpha times P2 divided by Pz, that is 1 minus alpha divided by 1 plus alpha times P2. If you solve, you will get alpha square P2 divided by 1 minus alpha square. Right? Because of the fact that alpha is much less than 1, we can write the same one as alpha square P2 only. So our Kp2 has come out as alpha square P2. Now we have to make the ratio of Kp1 divided by Kp2, and we will get, from here we have obtained Kp1 as 4 alpha square P1 and Kp2 has come out as alpha square P2. So alpha square will get cancelled out from here, and Kp1 and Kp2 has been given as 1:9. So from here we can write 1 by 9 is equal to 4P1 by P2, which is giving you the ratio of P1 and P2, which we actually are to calculate here as 1 time 1 divided by 36. So our P1 is to P2 is equal to 1 is to 36. And you can see from the options given here that option A is the correct option. So P1 is to P2 has come out as 1 is to 36. Very simple. I hope you have understood and enjoyed this session. So for more such sessions, you have to get connected with us, with Abdemi. Get registered and get connected. Thank you very much. Have a great day. Bye-bye. See you soon.